All right. So, and as usual, I'm sure, make some mistakes in the introduction. That's our tradition here, right? Okay. So Dr. Larry Denneau is from Manoa. He's been with the ATLAS team for a number of years. He is the ATLAS co-PI and senior software engineer. He was the chief software engineer of the Pan-STARRS MOPS program. MOPS is the Moving Object Processing System. I love that acronym because you take the data and then you mop it up, or you mop up all the moving objects. And then he adapted that over to ATLAS. And let's see, Larry has been poking at keyboards since the early 80s and received his BSEE from the University of Arizona, whereupon he quickly escaped to academia. He did a lot of software projects in semiconductor industry, medical scheduling, geophysical instrumentation, and even a .com internet startup. Now we got him back in academia, we trapped him, and he received his PhD in astrophysics from Queen's University, Belfast, and has enthusiastically joined the effort to protect the Earth from dangerous asteroids. So if we can give him a round of applause.
Okay, thank you. Alrighty, so I'm Larry Denneau, ATLAS co-PI. We've had a great year, and I'm going to tell you about some stuff that we've been doing. We're going to start out with things that go bump in the solar system, the ATLAS survey, which is my current project, and what we do and how we find those things that go bump. And then finally, a couple of interesting objects that our surveys detected in the last year. So we're going to start back in time, back to 1766, with a couple of German astronomers named Titius and Bode. And back then, our knowledge of the night sky was really limited. We only knew about the 7 planets, when there were 7 planets. Neptune was not even in the picture yet. And what they learned was, or what they noticed was that if you plot the planets going left to right with their distances from the sun plotted in a special way, so logarithmically on the y-axis, they form a pretty straight line, except that there's a gap in this pattern. And they thought, this looks like a mathematical relation that describes something physical, but it says that there should be something there. What's going on? And so they suspected that there might be a planet that ought to be at that distance from the sun that hasn't been discovered yet. And so they started, they described their relation. They said, we think there's something there. Astronomers, could you go start looking for something? And so based on that distance from the sun, they kind of had an idea of what its motion on the sky ought to be like. And in 1801, the first asteroid Ceres was discovered, and it fit exactly the spot it was supposed to be. And it was actually Gauss, the mathematician Gauss, who did everything, took the positions of the astronomers of this dot moving across the sky, and he worked out what the orbit should be and how far from the sun it was, and he basically got it right. But the thing was, Ceres is tiny compared to a planet. So what's going on there? People were still looking, and within a few years, they found 4 objects like at that position. So there's the first 4 asteroids discovered. And so in one sense, Titius and Bode got it right, that there's stuff there, but it's not a planet. There's something else going on. So about 100 years later, we know that the stuff that's there between Mars and Jupiter is this thing we call the asteroid belt. And so here's an animation of the known asteroids about 7 years ago. It's an animation from JPL showing the positions of all of those asteroids. And one thing you notice, so there's a huge belt between Mars and Jupiter. No surprise there, we know that. But there's a lot of these dots that also come into the inner solar system. And we're interested in those. So one thing about the asteroid belt, though, is why might there be, or why is there a belt of asteroids? Why should there be a belt at all? Why is it there? One thing that we now know about the early solar system is that it was filled with planetesimals and small asteroids everywhere, not just between Mars and Jupiter. And over the lifetime of the solar system, almost all of the asteroids that have been formed have been destroyed somehow or ejected from the solar system. So they've either hit a planet, they've hit another asteroid, or they've been ejected from the solar system. And so we know there's evidence of asteroids hitting each other, but there's a spectacular example of this from an object called P2010A2, which is a pan-stars discovered object. And when they saw the images of this asteroid, when it was discovered, it looked really weird. And here it is. It's really weird. What's going on? And based on the dust trails and the shape right at the asteroid, they realized that this is probably a small asteroid being hit by an even smaller asteroid, like 1/10 the size. And this is the dust pattern that's created by the two things hitting each other and the remnant dust that's still in the orbit there. So we know that asteroids, in fact, can hit each other, and we have examples of it now. And as far as things, asteroids getting ejected from the solar system, we know that that's possible. And a good example of how that works is something like a spacecraft gravitational assist. So when we send a spacecraft to the outer solar system, we often swing them by a planet so that they can pick up some additional velocity as they go by that planet and continue on their trajectory. The same thing can happen to an asteroid when it goes by a big planet, typically Jupiter. Jupiter is kind of the big bully of our solar system. And so when asteroids come into the neighborhood of Jupiter, they can be gravitationally perturbed so that they get closer and closer. And when they get really close, they can swing around Jupiter and be given a trajectory that sends them out of the solar system. Basically, they can get enough of a velocity boost by going around Jupiter that they can be ejected permanently from our solar system. So that can happen. And this ejection or velocity change is really sensitive to how close it comes to Jupiter. So something that swings very close to Jupiter can get a massive assist in its velocity, whereas a slightly more distant close approach may only get a modest boost. But either way, Jupiter and other large planets can drastically change and accelerate objects out of our solar system. So this leaves us with kind of a cartoon architecture of the solar system that I think a lot of us are now familiar with, right? We've got our planets, we've got an asteroid belt between Mars and Jupiter. The distances, of course, are not to scale. And then we've got this second asteroid belt called the Kuiper belt out past Neptune. And these two asteroid belts are really the leftovers of the original asteroids in the solar system. So they have managed to escape being ejected into the inner solar system where they hit something or hit a big planet or get ejected out of our solar system. They're like the survivors of the asteroids. Here we are 4 billion years after the age of the solar system. They're what's left. The Kuiper belt is similar, right? So between the Kuiper belt and the inner asteroid belt, the big planets are there clearing everything out. And what we have are two asteroid belts that are kind of the remainder of the original solar system asteroid population. And so as it turns out, what's left is 0.1% of the original asteroid population of the original solar system. And 99.9% of it has been ejected, has collided with something, or has been ground to dust from other collisions. These collisions, though, are still happening. Asteroids are still getting kicked into the inner solar system from the main belt or from beyond, and they're still colliding, as we saw from asteroid P2010A2. So these asteroids that get kicked into the inner solar system, they have orbits that they get converted from these fairly circular orbits in the region between Mars and Jupiter to something that is more of an elongated orbit that takes them out past Mars or toward Jupiter, but also brings them into the inner solar system. So here's an illustration of what those orbits look like. This is actually a plot of the 30,000 or so known asteroids that come within Earth's orbit. They're called the near-Earth objects. And so that's what the ATLAS project and planetary defense is all about. So planetary defense is the NASA term for projects that try to prevent collision of an asteroid or comet with the Earth. We know this happens. Here's the Barringer crater in northern Arizona. I went there about 5 years ago as part of a meeting, and if you ever get a chance to go there, it's super, super cool. It's big, but I mean it's even bigger than it looks in a photo, and it's really deep. It's surprisingly deep. Anyway, so we know asteroids hit the Earth. This asteroid that formed the Barringer crater was about a 50-meter diameter asteroid. So by our recent history, that's much larger than anything that we've ever known of in human timescales that's hit the Earth. And in the 90s, some astronomers who studied asteroids in the main belt started thinking that it might be interesting to try to figure out how many asteroids might there be that could come in and pose a hazard to the Earth. And so there were small efforts to start to detect and catalog asteroids that came close to the Earth. And in 1992, NASA convened a workshop, and they wanted to try to provide a goal for what astronomers could do in terms of assessing and understanding the threat from near-Earth asteroids. And their recommendation from this group, it's called the Space Guard Survey, was that astronomers and NASA should try to find and catalog 90% of the near-Earth objects that are bigger than 1 kilometer. So a kilometer is dinosaur extinction kind of size. And so we know that there's, well, we didn't know at the time how many of those there were out there. And the goal for Space Guard in 1992 was to figure out how many are there and can we find 90% of them and continue to work on that number to get it up to 99, 100%. So shortly after the Space Guard survey made its recommendation, astronomers Eugene and Carolyn Shoemaker and their colleague David Levy found a comet called Shoemaker-Levy 9. And this comet, when they found it, had been captured by Jupiter. So it had swung very close to Jupiter in the way that that diagram illustrated that something could be accelerated by Jupiter. But it came so close to Jupiter that Jupiter's gravity broke up the comet into this string of pieces. And what was more remarkable than that even was that the prediction for this string of comet pieces was that they would collide with Jupiter on its next orbit around Jupiter. It was orbiting Jupiter actually, so Jupiter's gravity had captured the comet and it was going to hit Jupiter like a year later. And so that was a fantastic prediction that was made. And a year later, the comet, the pieces of it hit Jupiter. And so here's a string of those comet pieces hitting Jupiter. You can see how big these explosions are, right? There's the Earth for scale. So these comet pieces, when they hit Jupiter, made an explosion that was like the size of Earth. And this was not a gigantic comet, right? And so this was an illustration that planetary impacts happen on human timescales. They can be really, really destructive. And therefore, it might be in our interest to try to find out where these objects are, and eventually, if we know that any are going to hit, do something about them. So a great recent example was in 2013, a 20-meter object impacted over the Russian city of Chelyabinsk. And this was one of the first events like this in the era of YouTube and cell phone cameras. And of the pictures and short videos of this thing were captured all over the place. And it was actually really instrumental in determining the precise trajectory of this thing as it came through the atmosphere. So from all of these different cell phone videos that were geolocated, they could, and that they were all time-stamped, they could figure out the precise trajectory of this thing as it came in from space. And it happened to be a very shallow, glancing trajectory, and so it burned up in the atmosphere and didn't really strike the ground intact, but it still did a lot of damage.
It exploded into pieces 19 miles above and 25 miles south of the city of Chelyabinsk. People thought it had missed them entirely until minutes later when the shockwave arrived. Shattering glass, crushing doors, and knocking some people right off their feet. More than 1,000 were injured.
How much warning did people in Chelyabinsk have?
None.
None. The reason for that is that it came from the sun side of the Earth, and telescopes cannot look there, right? We can only look at the nighttime sky, and so almost, half of the imminent impacts are actually going to come from that side, and so we're only going to, if something's on an impact trajectory, have, close to 50% chance of detecting that. But for all of the near misses, if we see those objects, we can then be aware of where they might be in the future and will they hit the Earth on their next visit. So in terms of the numbers, how big, how many, right? That's the goal of the Space Guard recommendation. And the question we're trying to answer is at different size regimes, so 10,000 meters, a kilometer, 140 meters, how many of these different sizes of objects are they? How destructive are they? And how do we go about finding them even? So that's where the ATLAS survey comes in. So ATLAS is a UH-operated, NASA-funded planetary defense survey. We are neighbors on Haleakala with another very prolific NEO survey called Pan-STARRS. And as JD mentioned, I started out at UH with the Pan-STARRS project. And there's also a very prolific NEO survey in Tucson, Arizona called Catalina Sky Survey. So those projects together account for the bulk of all of the discoveries of new near-Earth objects. And so our job is to find these objects before they do something to us. So within NASA, they've got now there's a thing called the Planetary Defense Coordination Office. If you've seen the movie Don't Look Up, everybody's seen that? Right, so that's the shield and sticker up there. I've got a pile of these, so if you want one, see JD after the talk. They look great on your laptop or your coffee mug or your water bottle or whatever. Anyway, so this is like a cartoon of NASA's vision for how planetary defense works. And projects like ATLAS and Pan-STARRS live up at the 1 o'clock position there. Our job is to search and detect these things. But after they're detected, the job's not done. You still need to know what these things are made of. How hazardous are they really? Will they come very close to the Earth in the future? Will they hit the Earth? And if they do, you need to figure out a plan for doing something. On the bottom left, you need to execute that plan. And then finally, after that's done, you need to assess how well did it go? Did you mitigate the asteroid? And what else did you learn? And so this process just continues over and over. And that's how NASA likes to think of planetary defense. So ATLAS is a system of 5 telescopes around the world. We have 2 here in Hawaii, one on Haleakala, one on Mauna Loa. Those were the 2 that were built first from our original funding. We asked NASA if we could build 2 more. And so we put one in Chile and one in South Africa. And the reason why we selected those sites is they give us longitudinal diversity. So when it's daytime here, it's dark there, and vice versa. And we also have latitudinal diversity. So we can see from the north celestial pole all the way to the south celestial pole. So there's no part of the dark sky goes unvisited by ATLAS. And then we have a 5th unit that's really a partner unit from the Canary Islands. They got their own funding from the EU to build a telescope like ATLAS. And we told them, if you build this, we'll reduce your data, we'll look for asteroids in the data, and you can be a partner in the ATLAS system. And so they just turned on a few months ago, and we're super excited to have them going as well, because you might think with 4 telescopes, the sky is always dark and clear somewhere, but it's not true. We're actually weathered out somewhere a lot of the time, and to have more telescopes gives us more weather redundancy so that we can look at the sky more frequently. So there's the ATLAS dome on Haleakala. If you've been up there, we're in the little science city up there. We're a small telescope, right? So we've got the big kids near us. We've got EOS, we've got DKIS, we've got the 2 Pan-STARRS telescopes. We're just a tiny 16-foot dome up there doing our thing. And here's what our telescope looks like up close. The telescope itself is only a little bit bigger than a person. And the whole dome could probably fit in a big garage. But that's all we need. Our telescopes, despite being modest in size, they have a single very large CCD. They have a wide field of view on the sky, and we make them as sensitive as modern technology will allow us to make these cameras. They all operate robotically, so there's no person at a console operating these telescopes. The telescope scheduling happens completely automatically. The domes open up when the weather's good and it's at sunset. They execute their observations. The data is automatically sent to UH Manoa, where we reduce it. And what comes out is a screen that a person finally does have to deal with, which is a list of candidate objects that are likely new near-Earth asteroids. And those are what we review and then submit for further observations by the rest of the community. So here's what a typical ATLAS image looks like. So this is about 5 degrees by 5 degrees on a side. For reference, that little yellow dot at the top is the field of view of JWST. And this one big square is a single ATLAS image. And there's a full moon. If you could put a full moon in our image, that's what it would look like, but we never do that, of course. And then finally here, it's not, is it moving? Yeah, it is moving, okay. That's what a typical asteroid looks like moving in our field. So if you were looking at the whole image, there's no way you would see this. But if you have a cutout, you can see the asteroid moving there. So our software, so each telescope takes about 1,000 of these pictures every night. So we're getting 4,000 to 5,000 across the 5 telescopes. And we look for dot to dot to dot, things like that moving that are unknown. There's a catalog of all of the known asteroids and all of the 35,000 known near-Earth asteroids. So if we see something moving, we first check against that catalog to see if it's known. If it is, we don't worry about it immediately. But if it's unknown, we want to submit those discovery observations as soon as we can to an organization called the IAU Minor Planet Center, who coordinates follow-up observations of these new asteroids. So ATLAS doesn't really do that. Our job is to detect them the first time, and once you know roughly where they are, there are other telescopes that are better suited to following a single object as it's moving across the sky. Our job is to cover as much sky as possible and look for things that where we don't know where they are. So to kind of just to illustrate how much sky we cover, this is when we were just operating 2 Hawaii telescopes. This is a single night, so we're able to get the whole northern hemisphere from 2 telescopes. And now that we have 5 telescopes operating, this is what we can do in one night, right? We can cover the entire night sky with all 5 telescopes. So that's pretty cool. Okay, and planetary defense is more than just ATLAS finding stuff. We're just the first step. Once we find something, as I mentioned, we need follow-up observations to confirm the asteroid, right? We need to see it for maybe maybe dozens of observations over the next 24, 48 hours to be sure that we have a real object and that we know its trajectory enough to say what kind of orbit it has. So that takes observations by many other organizations, and they're all contributors in the whole effort. And then finally, once the trajectory and the orbit are confirmed, then the object becomes cataloged at the Minor Planet Center. And from there, other things happen, like JPL gets involved with all of the new asteroids, and they do a very sophisticated hazard analysis, which is this asteroid, where is it going to be relative to the Earth or other planets over the next 50 or 100 years? And they publish this asteroid, how likely is it to be close to some other, to Earth or some other planet? And that's part of the hazard analysis, and the ones that come close to the Earth, of course, are super interesting. Okay, so we've got projects that look for near-Earth asteroids. We get orbits out. How is the whole effort going in terms of filling out that table of sizes and how many there are? So first of all, this is just a list of asteroids that have been detected in space before they've hit the Earth. And so prior to 2008, that had never been done. In 2008, Catalina Sky Survey found the first object in space before it hit the Earth called 2008 TC3, and since then, other projects have found about a dozen more. And so here's just kind of a smorgasbord of them. In the red, though, it was something that's worth noting is that all of these objects are tiny, right? 4 meters, 3 meters, 1 meter, 2 meters, 3 meters. And basically, there's a lot more small things in nature than there are big things. And so these objects are hitting the Earth all the time. They're completely harmless. They make a super nice shooting star as they go across the sky. So this one is really cool. This happened right over Toronto a few years ago. And these objects are so small that they're only discovered hours before they hit the Earth. But right after discovery, it was predicted that it would be right over Toronto. Rob Warwick, who works for Pan-STARRS, Hayden knows him, I'm sure, it's like right above his house. They said, oh yeah, at like 5 in the morning, go point your camera at this spot on the sky, you'll see an asteroid hit the Earth, and there it was. So that's super cool. We know how to do this, and fortunately, we're getting lots of practice with these little tiny objects, and so far we haven't had a big one that we've had to deal with yet. In terms of filling out the table, how are we doing? So bigger than 10,000 meters near-Earth asteroids, they're all accounted for. We don't think there are any more out there that can be discovered. We've looked everywhere. If there were any out there, they would be obvious, and all of the surveys operating over the decades they've been operating now haven't found any more this big, so that's covered. The 1 kilometer and bigger, so these are still dinosaur killer kinds of asteroids. We've met that goal of 90% of the Space Guard 1 kilometer asteroids. We're up to about 95% now. There's still some arguing about whether we're at 95 or 96 or something, but they've basically all been accounted for. And one way we know that is that we're simply not finding anymore. There's like the plot of the discovery of them has shot up and then basically has leveled off, and like every year maybe 1 or 2 more get found. And there's a total of like 900 of these out there, and we've got 95% of those accounted for. So there'll be a few more trickling in over the years, but basically we know where those all are. At 140 meters, which is the next goal after the 1 kilometer goal, we're only about 40% complete there. So there are tens of thousands of those out there that we don't know about. And the focus of near-Earth object surveys right now is to make up as much ground as we can on the 140 meter size. So that's no longer, you know, humanity-threatening kind of size, but it is big enough to take out a very large city, a small country, a big region if it's populated, and so that's an important size that you know, that we want to consider. Below that, they will be more frequent. There's a lot more of them, as you can see, like down at the 50 meter size. There's some 200,000 estimated asteroids out there, right? We're simply not going to find them all. And for those, the strategy would be detect them before impact so that you can evacuate an area if that's the right thing to do. So there's kind of different strategies depending on how big they are and how much time you might have before they impact. And at the small size, 10 meters, so this is still bigger than the things we've been finding, there's millions and millions of those. And we're never going to catalog those. We simply will see them. And if we know they're going to go over a populated area, they're not going to do that much damage, but we can tell people to get out of the way. And, you know, but at 10 meters, not a lot of damage can happen. That's smaller than the one in Chelyabinsk, which caused some damage, injured some people. So the Chelyabinsk video, nobody was hurt by the asteroid, but when it exploded in the atmosphere, what happened was there was this huge flash when it came into the atmosphere. Light travels faster than sound, and so everybody ran to their window to see what this was, and then the shockwave hit, right, and blew glass into people. So 1,000 people were hurt from falling, from broken glass, whatever. And it was from the shock wave going through the atmosphere, not the actual asteroid impact. Okay, so on to some interesting objects. So the first one is an asteroid named 2024 YR4. So the names of asteroids are kind of funny. They're the year they were discovered and then a letter and number code that indicates when in the year they were discovered. This one was Y. The letter Y means the second half of December, so it was an asteroid discovered sometime in the second half of December of 2024. And so here are the ATLAS discovery observations of it. So it's a little thing moving quickly left to right. So this covers about time of about 30 minutes from the first exposure to the last exposure. And if you look carefully, it's probably hard to see, the asteroid is moving so fast on the detector that's got a little kind of football shape. It's not a dot, it's more of like a little oval. That's just because over the 30 seconds of the exposure, it's moving across a few pixels, and so it has a funny shape. So this is a totally, at the time, garden variety near-Earth object discovery by ATLAS. We see these all the time. And at the time this was submitted, I think I was the person who was at the computer at the time. I sent the observations in, and it was a routine discovery. No problem. So here's the orbit of the asteroid. So it's one of these elliptical orbits, and so it goes out well past Mars, almost to Jupiter. It's a 4-year orbit, and you can see, so Earth's orbit is the blue circle here, and on its orbit, you know, twice it crosses Earth's orbit, and so it can have a couple of opportunities to come close to the Earth on its regular orbit every 4 years. And if the Earth and the asteroid are in the same place at the same time, bad stuff can happen. So it turns out, analysis by JPL, who does this kind of thing when objects are discovered, they realize, of course, for us to discover it, it was already fairly close to the Earth, but they realized that in 2028, it was going to cross our orbit, not in a hazardous way, but in 2032, it was going to have a very, very close approach with the Earth. Close enough that based on how accurately or inaccurately, based on your point of view, that we knew the orbit, we could not rule out that it would miss the Earth. There's a small probability of impact. So here's how big the thing is. So we didn't know its size very accurately at the beginning, so it was somewhere in this size between the black circle and the gray circle, something like 60 meters in diameter. So that's pretty sizable. It's much bigger than the one in Chelyabinsk. If that were over a city, it could do a lot of damage. It was bigger than the one in Tunguska that flattened the trees in Siberia in 1907, I think, and bigger than a jumbo jet even. So a sizable rock. So in planetary defense, in terms of, so a big thing in planetary defense is these objects ultimately affect people. And so a big part of the program is communication of risk to the general public so that they have a way of understanding how dangerous an event might be, where to set thresholds for when you notify people and don't notify people. Because as you might suspect, if you mention that an object has a chance of hitting the Earth, sometimes the news, the internet will go nuts, right? And I'm going to show you that in a second. So there's a thing invented called the Terrestrial-impact hazard scale, which is just a simplification of some of the hazards that that let us get from orbital parameters in size to do you have to worry. And so 2024 YR4, this asteroid, it's small, so it's kind of living down in this region here, but its probability of impact, so this is 1%, this is like certain impact, this is 1%, this is 1/100%, and so on. 2024 YR4, right after discovery, hovered around this 1% chance of impact. And so that pushed it into, from the 0, which is like, don't even have to worry about it, straight into the yellow here, which is, oh, we might have to worry a little bit. And so the yellow means it's now an object of interest. And there's a kind of a sibling group to, not to NASA, but it's a partner in the planetary defense effort called the International Asteroid Warning Network. And what they do is they kind of consolidate all of this information, the scientific part, communication part, and they also integrate with other countries and figure out, based on where this thing might hit the Earth, how do we present the information in a way that explains clearly what's going on and what the risks are, and so on. And so since 2024 YR4 was the first object to go from 0 into the yellow, this organization, they call themselves IWAN, issued their first ever level 1 alert for this object. And the alert has all of this information in it, but in the red box is is the good stuff, right? It had a 1.3% chance of impact on 22 December 2032. And so they issued this, and this activated when this alert is issued, it activates some things within NASA, that some things have to be started. They have to consider some things, like, should we try to send a spacecraft to it? We have to study it really hard. We need more observations of it to get the orbit totally nailed down. And so you might be thinking, what does a 1.3% chance of impact mean, right? How do you arrive at that number? How do you believe it? And I was thinking on the way here, I've talked to other astronomers about how to convey that sense of impact. And some use it, some think of it like a hurricane prediction. Like early on, you kind of don't know where the hurricane's going to go, but as more time goes, you know with more certainty where the hurricane's going to go. But still, with a hurricane, at the last minute, it could veer off in some other direction. So it's not quite a good analogy. And I was thinking a simple analogy that might work would be, imagine if you just had a football and you threw it really far as you could, so 50, 60 yards or something like that. Could you predict exactly where on the field it's going to hit, right when you throw it? The answer is no. You might say, oh, it's going to hit over there somewhere. But if you took pictures of you throwing the football and you had pictures of it leaving your hand, you would know more accurately where it's going to hit on the field, right? And if you had even more images, you would start to narrow down where that's going to hit very, very accurately. So that's how this prediction probability kind of works, which means that based on our knowledge of the orbit, right, the asteroid's not doing anything different, it's just on its trajectory, but we have imperfect knowledge of exactly where it is because our observations are not perfect, that we can, based on the statistics for where this object could be within those uncertainties, 1% of the time its orbit is going to hit the Earth. And the way to make that number get smaller and rule it out or rule it in is to keep observing it and let that trajectory become more and more understood over time. That's the only way you can do it. And so the problem with YR4 was that we only had a few more months to observe it, and then it would be gone until 2028. The reason for that is it's small, it's moving away from the Earth, and then it would be on the other side of the sun. So we kind of only had a few months to figure out what was going to happen to this thing. And by 2028, if you had to launch a spacecraft to do something about the asteroid, it might be too late. And so there was some pressure on, should we act now in that regard? Should we just wait for the measurements to come in? Because most of the time, the measurements will say that this object's not going to hit. Anyway, efforts within NASA they started thinking about the spacecraft thing, but mostly they wanted to let the observations come in. And while they were doing that, more calculations happened, and they figured out that if this were to hit, this is where it would hit. So kind of along the equator. It actually, I mean, there's even a chance that Hawaii is almost on the front end of that, but mostly it would go South America and Africa. And the way to think about how this works is where the asteroid could be is really, think of it as a really, really long stripe in space. And the uncertainty in the asteroid's position means that it can be kind of anywhere along that stripe. And so that's what's conveyed here, is we don't know where along that stripe the asteroid is going to be when the Earth crosses its orbit. And that's why the impact location falls along a line like that. Anyway, so we kept observing it. Other telescopes, the more powerful telescopes that could see this thing as it was receding from the Earth. And in January, it was late February, IWON issued the all clear. They said that based on observations, so not going to hit, that they could rule out, beyond any statistical uncertainty, that this thing was not going to hit in December 2032. But they cannot rule out an impact with the moon still. So right now it's got like a 5% chance of hitting the moon on that date. So the moon is still kind of in the area where it might be. And so it's still interesting in that regard. And a thing, if you need things to worry about, is you can imagine this thing could hit the moon, liberate a lot of stuff on the moon. The moon doesn't have much gravity, right? So these rocks that might be liberated from the moon would still be on a trajectory that could bring them to Earth. So it could make what seems like not a problem into a problem again. So we don't know. So we actually care if it's going to hit the moon. And if it did, we'd want to know exactly where it's going to hit. Is there anything we need to do? So I want to talk a little bit about this 1% business again, because when all of this was happening, in astronomy, there are a lot of skeptics out there for whatever you're doing sometimes. And with this kind of prediction, something that happens, and it happened with this asteroid, is the impact probability started out at 1%. And then over time, as more observations came in, that number went up. And it got as high as about 5%. And then all of a sudden, it went down to 0. And we know that's how it works usually. We expect that to happen, but it's not something that is easily conveyed. And so if you're a skeptic to begin with, we hear things like, oh, you astronomers don't know what you're doing. How does the probability go up and go down? Do you guys, are you any good at statistics? What's going on there? So this is an attempt to try to illustrate how this works, right? And so imagine, so this is December 22, 2032. And so this red oval is when the Earth goes by the asteroid. That's where the asteroid could be, based on the knowledge we have. It could be anywhere in that ellipse. And the Earth is about 1% of that area, right? So based on where the asteroid could be, there's a 1% chance that it'll be over the Earth. That's how that works. If our knowledge of the orbit improves, we're going to shrink this red oval, right? And when we shrink the oval, it starts to look like this. Now Earth is a much bigger fraction of that oval. The impact probability has gone up to 5%. The asteroid hasn't done anything different. We just have better knowledge of where it's going to be. But based on these contours, I think you can get an idea of where this is going. At some point, that oval will be reduced off of the Earth, right, to its natural center of the distribution. And now the probability of impact has gone to 0, right? So it grew because the Earth remained in the oval. But once the oval gets so small that the Earth's no longer in it, then the impact probability immediately goes to 0. And so that happens a lot. And we expected it to happen with this one. And it just took more time than folks were comfortable with. It took a couple of months for observations to come in to finally nail down and rule out the impact in 2032. So while all of this is going on, so I have to say something about fake news and this kind of stuff. There's people who refuse to believe that it's not going to hit, right? And so you have all of this like strange AI-generated, wacky stuff on the internet. It's people are willing to put anything out there. You can get really good production, value or production quality now with cheap tools. So they make great-looking videos that say all of this, doom and gloom stuff, and a lot of it's just not true. So it's a struggle to stay up to date and know what's true and what's not true. And YouTube and the internet are not the best places sometimes to get that information. There's a lot of great stuff out there, but you want to try to corroborate that information, with places like NASA, Scientific American, Smithsonian, and so on, which will often have similar information, and then you can build the picture of what's going on for real on your own. Okay. Any questions so far? No? Okay. Yeah.
Could you explain that algorithmic distance of the planets on that initial chart? You know, a planet where they discovered that there should be an asteroid belt. I don't understand why the planets would be algorithmically on a straight line.
Okay, I can.
And please repeat the question so they.
Okay, so the question is from the very first slide in the Titius-Bode relation. What's going on there, right? What is this algorithmic distribution of the planets? And so they basically took the logarithm of the distance from the sun and added a little correction for Mercury, and then basically all of them fall on this line after that when they're logarithmically spaced. But there's some things I didn't say about it because I didn't want to go into it too much tonight. But so one is the interesting thing they found is there seems to be this gap, right, where there ought to be something, and in their counting of the planets, there's not something there. So that was the basis for their conjecture that there ought to be some stuff at that position in the solar system, right? But it turns out that Neptune is not on that line. Neptune is off by a little bit, and Pluto, which was believed to be the 9th planet, is even more off. And so the relation that they believe they found is more of a coincidence about the planets than like a law of nature or a law of how the planets should be distributed. Basically, you can think of if you form a giant planet like Jupiter, Jupiter then will dictate kind of where other things can be relative to it. You can't have another planet that's really close to Jupiter, and they will naturally space out in a way that looks like that law, but they won't be precisely following that law. You'll always have this weird little correction factor for the inner planet and so on. So, you know, they only had one solar system to work with, and so they did the best they could. But we now know from exoplanet systems that the law doesn't really hold the way they drew it up. Does that help? Thanks, great question. Okay, I'm going to talk about the other super cool object that ATLAS has been involved with. This one is still in the news. And let's jump right in. So when we send stuff to the Minor Planet Center, so here are the discovery observations of another interesting object. This one looks different, if you are looking closely, that there are a lot more stars in the background on this one than there were in the previous one. We found this looking in the galactic center, like in Sagittarius, where it's very, very difficult to find things. But we found it. And when we send stuff, they get a funny name that's just an internal ATLAS name, this A11PL3Z. This was June 30th when we sent that in. Again, I was at the wheel when this went in. I was just lucky. But I sent the observations in. And so there's a picture of the part of the galactic plane on the sky where we found it, right? So we're kind of lucky in that it was in a relatively less dense part of the sky. If it had been over there, it would have been a lot harder. But we did find it, and there it is again moving. And so normally when we send in near-Earth object candidates, we kind of pay attention over email to see whether they're confirmed, they've been followed up and stuff. But for this one, on June 30th, my co-PI, John Tonry, and I, we had to go to Mauna Loa on the Big Island to service our telescope up there. And servicing that telescope is very complicated. So there's where the telescope is on Mauna Loa. So this is the NOAA facility on Mauna Loa. It's the clean air monitoring facility. They have a whole bunch of atmospheric experiments up there. We inhabit a little nighttime astronomy dome up there. But Mauna Loa, and so what we had to fix was there's a piece of the top part of the dome that rotates. There's a thing called a finger that attaches to those orange, what are called slip rings. One of them broke off. And so we were no longer able to operate our dome, and so therefore we were completely shut down. So in 2022, there was an eruption on Mauna Loa. And so as complicated efforts to get up there, we can only get up there by helicopter. And so planning to go up there is we have to go super early. We fly over from Honolulu first thing in the morning, fly to Kona, we get in a helicopter in Kona. 20 minutes later, we're up at the dome. It's really cool, but it's kind of a taxing day because when you're up there, if the weather starts to change, you must come down, right? There's no way to get you down. And so you're always kind of watching your watch. You're making sure you don't start a task that's going to leave everything broken because the helicopter company may say, you got to come down in 20 minutes. So it's a stressful environment, and also you're at altitude. Everything is hard. Anyway, so we went up there to fix the telescope. So anyway, but back in 2022, we'll take a short detour about the eruption. So at our telescopes, at all 4 of our telescopes, we have this weather station that we've built that has a Canon DSLR that's pointed at the sky. And we take pictures of the sky during the daytime and during the nighttime. And so this is what our telescope, or just our camera sees. And we use this to tell us what the sky transparency is, what the weather's like all the time. And we know the Pan-STARRS folks love it because it tells them how the weather is on Haleakala, what parts of the sky they should avoid, and so on. And they're super useful to have up at your telescope. On November 28th of 2022, this is what the all-sky image saw. It was cloudy and rainy up there. And so what you're seeing here is, this is the moon setting. So the moon is just this bright splotch that's sometimes obscured by clouds. This is the radio tower that's next to the NOAA station. So they've got like a 75-foot high tower that's doing something, but it's got a red light up there. And so you're seeing that reflected in the water droplets up there. Anyway, so later, the next day, we had similar weather, and then the eruption happened. And so this was the video, this is a time-lapse video, this is not real time, of the sky from our observatory as the eruption was happening uphill. And it's just super cool. I love this video. And I've wanted to show it like inside a planetarium, just like to be inside the volcano when it's going on. And anyway, so it goes on for, it's about 2 hours of video in time-lapse. And then finally it's daytime, and that's when the lava hit the road and the electrical power lines and knocked everything out. And so that's our last frame of video for that. Anyway, so there's the eruption. I'm sure many of you have seen pictures like that from that. You can see here the path of the lava. So this black line right here is the road that goes up to the NOAA station, and the lava has crossed the road in 2 places. And so that's why it looks like this. And we have to take a helicopter up there. Anyway, so we were up there dealing with a broken telescope up at 11,000 feet while this new object was being considered and followed up by the rest of the community. And when we got back to Honolulu, I checked my mail, and it blew up with this thing A11PL3Z that I had sent in the night before. And some of the messages that are really interesting say that this object, the orbit that we're computing for it, has a high eccentricity. And what that means, what it usually means is there's something wrong with your observations. And so when you see this, they're asking you, can you check your observations? Something's funny. But it turns out that additional observations had the same behavior. And so let's talk about what high eccentricity means in the observations. So we're gonna talk about orbits a little bit. So most orbits, of a small body around a large body are this mathematical construction, right, that describe some parameters that say what the orbit, what the motion of this object is like from around the big object. So it could be like an asteroid around the sun, or it could be a moon of Jupiter around Jupiter, and so on. But one of the parameters, one of the fundamental parameters of an orbit is this eccentricity number E, and an E of 0 means that the orbit is basically a circle. And as the eccentricity goes up, the orbit becomes squished. And so a typical near-Earth object that comes within Earth's orbit but goes out past Mars towards Jupiter can have an E of something like 0.6, that's common, 0.8, 0.9 is common. But you can see at 0.9, the eccentricity is squashing the orbit. And so if you remember your high school math and conic sections, and when you took conic sections, you probably thought, when am I ever in my life going to use conic sections? And so here you are, conic sections. So the path of an object around another body can be described by a conic section, right? So you have your circle. If you tilt the circle on a cone, you have an ellipse. If you keep tilting it to where you can't make a circle anymore, right at that spot, you have a parabola and a parabolic orbit. Past that, you have a shape called a hyperbola. And so that's called a hyperbolic orbit. And what happens at the parabola is that this E number becomes exactly 1. And when you get into the hyperbola, the E number gets greater than 1. And so when my email said high eccentricity, it meant that it has one of these hyperbolic trajectories. And the thing about the hyperbolic trajectory is that it's not closed. The object on that path will not come back. So for that to happen, the speed of the object coming in has to be so fast that the sun cannot capture it and keep it in its orbit. So that's what is so important and so interesting about a hyperbolic trajectory for this object that Atlas found is it meant that the object was not from our solar system. It was coming in too fast and going out too fast, could not be bound by the sun. So a day later, after lots of observations and lots of discussions over email, confirmations of stuff, the announcement of a new object by the Minor Planet Center. It has two names. The first is a normal comet name, which is comet C/2025N1. So that's one of those cryptic planetary body names. But it's also called 3I, 3 being it's the third interstellar object ever discovered. The first one was Oumuamua by Pan-STARRS, and then another comet called Borisov back in 2019, which is kind of similar to this one, but there's some differences between across all of the objects. So this plot here shows that hyperbolic trajectory of all three of those interstellar objects. So the widest one here, this black line, is our object, 3I. Oumuamua comes in very close to the sun, gets swung around the sun. Borisov has a similar hyperbolic trajectory. So those are not orbits that are captured by the sun. They're coming in too fast and they're going out too fast. So that's cool. We have another visitor from another solar system. And what do we know about this so far? It has a thing called the hyperbolic excess velocity of 60 kilometers per second. So that excess velocity means if you were coming in fast enough just to be at the escape velocity where you were no longer bound to the sun, how much faster than that are you going? That's how much faster, 60 kilometers per second, or 130,000 miles an hour. It's still on its way in, so it's going to come closest to the sun in October of this year. And it's one of the most massively observed objects that I've ever seen. I mean, there are constantly observations going on by everybody trying to understand what is this thing made of, what is it doing, and it's just been, from week to week, our knowledge of this thing is changing. So it's really cool. So here's where it is like today. So it's halfway between Mars and Jupiter right now, and you can see it's going to come close to Mars. There's a nice video put out by Catalina Sky Survey showing where this thing's going to be. So there it's coming in, and it looks like it's going to hit Mars, but it's actually a bit above Mars when it goes by. And that's perihelion there where it's closest to the sun, and then it's going to be on its way out. And so our window to observe this thing is going to be really like the next year or so. And there's going to be a period of time coming up when it's behind the sun and we can't observe it when it's close to Mars. But when it's close to Mars, there are some efforts to try to get some of the spacecraft in orbit around Mars to go and point at this thing when it goes by. And those could be spectacular observations if they're able to pull them off. So we're hoping for that. So what else do we know about it? At the beginning, when we just had the original observations of it, our size estimate was only based on these wide field telescope measurements where you couldn't see the coma. And so based on that, we thought it was kind of big, maybe as big as 10 kilometers. But once we realized it has a coma, then the size estimates become much more difficult. And so right now, the size for the nucleus of this thing, so the hard, icy part, is somewhere like 3 kilometers, maybe a little bit smaller. It's a comet. It's got this emission of stuff coming out, so gases and dust are being emitted. The main emission from the comet is not in the tail direction. It's actually toward the sun, which is unusual. But this object has been cold, really, really cold for millions of years, right? And so we don't know what's going on inside the body of the comet. We don't know exactly what the surface looks like after millions of years of being bombarded by cosmic rays and staying very, very cold. So the way stuff is released from this comet may be much different from how we're used to in our solar system, where every only 100,000 years, a comet gets warmed up by a visit to the sun. So this thing has been cold for so long, we don't really know how it's going to outgas as it comes by. But a lot of familiar things are present. CO2, water, carbon monoxide. The carbon dioxide to water ratio is unusual for this comet. It's very large. So that's something that's different about it. We don't really know what that means yet. It's still under development. But stay tuned and we'll learn more. So there's some nice images there from former IFA astronomer Dave Jewett, who's at UCLA, who's expert at following these things as they happen and gets Hubble and JWST time to image them and study them. So super cool. But back to fake news. I was a little bit demoralized, trying to come up with slides for this one. Going on YouTube, there's this astronomer from Harvard, Avi Loeb, who's made a little name for himself. He started with Oumuamua, but he's convinced that it's alien technology. And 3I, he's convinced, is alien technology. And once that gets out there, people latch onto it and want to believe it. I mean, personally, I would love if it were an alien spacecraft, right? But, extraordinary claims require extraordinary evidence. This thing looks and acts like a comet. He even made a prediction that it would slow down and then change its, trajectory toward the Earth. That has not happened yet, but they're still out there. He's still saying this thing is weird, it could be alien. There's people latching onto that saying, they're coming for us. I mean, it's one thing to say this is alien technology, but how you get from that to they're coming for us is a bit of a leap to me. So, but if you go out on YouTube, there's tons of stuff like this. And I'm just imagining, a person who might be interested but doesn't know that much, when they see this, it's hard to blame them for not understanding anything. It's really scary. So anyway, so beware when you see that kind of stuff. As far as we can tell, it's a comet. So we're getting to the end here, and I just want to leave you with this object. There's one thing I read about it that for me I just thought was kind of amazing, and that is so here's a study by Hopkins on the trajectory of this thing through the Milky Way. So it's hard to see, I think, here, but there's some yellow lines, that's the path of our solar system over many millions of years around the Milky Way, right? So we're kind of out at towards the edge of the galaxy, and the red lines are the trajectory of, we think, statistically, of 3I as it might have gone around the Milky Way, and it's been doing that for a very long time, as far as we can tell. If you turn the Milky Way on its side, you can see that the sun's trajectory, the yellow, it's really all within this very, very flat part of the Milky Way. It's really locked into the plane of the Milky Way. But 3I spends most of its time a bit above and below that very narrow plane of the Milky Way. And what that means is that 3I is likely to be part of what's called the thick disk of the Milky Way, where the stars are much older. And therefore, if it's from that part of the Milky Way, and came from one of those stars, this object could be 10 billion years old, older than our solar system. And to me, it's just amazing that this thing could be out there basically in cold space, probably cruising through a handful of solar systems, but doing this for billions of years, and now it's here, and what can we learn from it? It's just, I don't know, kind of, to me, humbling and amazing all at the same time. And it's just a super cool thing. So, but back on Earth, ATLAS is still doing its thing. We're going to continue to look for objects. Hopefully we'll find stuff as cool as 2024 YR4 and Comet 3I. And some takeaway thoughts are that ATLAS is part of this global planetary defense effort. And we found the big stuff, and we're working on the smaller stuff. Efforts continue. UH is an integral part of that effort. So at IFA Manoa here on Maui, on the Big Island, all of UH is instrumental in making all of this happen. And then finally, when we designed the ATLAS survey, we deliberately said we want to observe as much of the sky as we can all the time. Who knows what's out there, right? And when you do that, you find some cool stuff, so keep looking. And a last thought is that the stuff we do is really, the communications aspect of it is really important in explaining what we do, how to explain the planetary defense threat to people. And so getting the word out there, events like this, outreach in general, are all super important in the planetary defense effort. So I thank you for coming out and for being part of the body of people that are just interested in what we're doing. Thank you very much. And with that, I think I'll stop and take more questions. Thanks. There's a couple of questions up front. Go ahead.
Of course, the question about the 3I. Is there any theory as to what is causing it to travel at that speed? And is it going in the same direction as the rotation of the galaxy, or a different direction?
Actually don't know. So the question is, what is causing it to go at that speed? And I believe it's just the sun has its own trajectory through the Milky Way, and this object, being very old, has been on its trajectory, and that's just the difference in the two trajectories. So one thing about this, so there's a part of the sky in the northern hemisphere called the solar apex. So that's like, in a meteor shower, there's the, what is it called? The radiant, yeah, that's the direction that we're going to, right? And everything seems to be coming from. The solar apex is the galactic radiant, basically the direction the Earth is going. And it was believed that future interstellar objects would likely come from that direction because that's the direction the sun's going. This one kind of came from the other side, and I think is catching up to us. And so what does that mean? I actually don't know the answer to that. In the back.
Do some of these extra solar system objects, asteroids, do they come in slow enough that it would be grabbed by our sun and just become another part of an asteroid belt?
I can't think of a reason why it's not possible. But I think that for them to have been floating around out there, they've got to be moving pretty fast because they're likely to encounter other solar systems or graze by them. And so their initial velocity, kind of, their escape velocity from wherever they're going has to be fast enough to allow them to keep going. So I think it would take a really precise, unlucky trajectory for one of these to kind of come in. I think it's more likely for them to hit something than to be gravitationally captured by them. And that's something it's a tiny, tiny thing we do have to worry about. Is not just our own solar system's objects hitting the Earth, but now that we know these are out there, one of these could hit the Earth, right? The odds are small, but still it could happen. And the thing is that the energy is mass times velocity squared, right? And the velocity squared of these things is very large because they're coming in so fast. So if they were to hit, it could be a lot more damaging than a solar system object of the same size. How about over here? Thanks.
Yes, so, and this is kind of a math question. So you identify an object. We saw the pictures of the objects moving. At that point, you don't know the degree to which they are moving towards you or away from you.
Right.
Because you see them that way. So the speed that is judged of the object would be dependent on how the angle, whether it's moving towards you or more horizontal.
Right.
So how do you account for that as you're making the assessment?
So the question is, how do we, from a short number of observations like we have, know the radial velocity, right, of this object relative to the Earth? The answer is, from those 4 observations, you don't know very precisely. It's unusual to have that kind of information. You have some guesses, but there's a whole space of solutions that just from 4 observations your orbit could have. But over time, what you need to collapse that information mathematically is observations over a longer amount of time or from parallax. And one way to get parallax is just the Earth rotates, and now you're looking at the same object from another vantage point 6 hours later. That's enough, right? So these objects that are newly discovered, basically, when they're observed 6 hours later and 8 hours later from a different point on the Earth, from a slightly different vantage point, that's enough to collapse the position so that we know the radial velocity. Yeah, right here.
So you had mentioned I3. It's got looks like it has a lot of water, a lot of H2O, a lot of carbon dioxide. How do you make those estimates, those guesses, whatever the right curve is?
So one is we do see water coming off of it, right? So there's a paper that, I don't know if the paper is out or only the preprint is out, but it's, so there are JWST infrared spectral observations of the comet. And so they show a huge CO2 signature, but there's also a water signature, a CO signature. So, and there's a bunch of other things coming out too. So we know like all of the basic stuff we see in comets is there. And there's questions about how the water might be released, right? So the crust of this thing is probably a lot different from other comets that are in our solar system. And so we're not seeing a lot of water right now, although we're seeing some. And we think that inside the comet there's a lot of water, but it's basically captured in this like really hard crust. And that what we're seeing in the reason why we see water is that instead of water vapor coming off, is that particles are coming off, and then once they're off the comet, heating up and releasing water that way. And so we're trying to, the models are not certain for what's going on. We're trying to build a picture of what's the surface of this thing like, what's inside it. But we don't have a really good reason yet to think that the water and CO and CO2 abundances are radically different from what we see on Earth, because we do see all of those things. Over here.
Yeah, so being able to use infrared, you can almost tell what chemically is coming off of 3I Atlas by how it presents itself in infrared. Like you can tell the difference between CO2 and oxygen.
Yeah, so they have so the question is, can you use the infrared to figure out chemical composition from 3I? And so JWST has, their regular cameras are infrared detectors, but they have this thing called the integral field unit spectrometer that basically presents an array of spectrographs at each pixel as they observe the thing. So you get a spectrum at every different point on this image. And so from there they can, the spectrum gives you, the response at all of these different spectral lines. Yeah, so they can resolve, they can tell out in the tail this kind of thing is happening, close to the nucleus this kind of thing is happening, right at the nucleus they're seeing other stuff. And so that's letting them build their picture of what do we see right at the nucleus, what do we see out in the tail, and it's different, right? So that's where this idea that maybe particles are being released from the surface and then later they're expelling water vapor, right, based on what, yeah, sure.
How much more difficult is it to see interstellar objects as compared to near Earth objects?
They look exactly the same. So this, yeah, for us, I mean, we thought when we found it, we thought here's a near Earth object. I think after more time, we would have realized it's cometary because we would start to see it puff out a little bit. Atlas is not the best thing to observe a comet. Right? All we see is that it might be very, very slightly diffuse, but that's it, because our pixels are kind of big on the sky. But, but it's enough to say that this thing's fuzzy, and then a bigger telescope, even if Pan-STARRS can do a great job with it, can resolve the coma much better than we can. Yeah.
What determines the E value? E like less than 1?
So the less than 1 means that the path is closed, right? So from a conic section point of view, it means that you've made your intersection with the cone produces an ellipse or a circle. But as you tilt that plane over the cone, the path is no longer closed. And the extent to which you mathematically form like an even straighter line makes the eccentricity go up. So as your intersection with the cone becomes less and less curved, the eccentricity goes up. And from a orbital point of view, it means a velocity, an incoming velocity that has to be faster in order to maintain that.
I'm asking what determines that?
Repeat the question.
Oh, okay. So the question is, what determines the E value? So it's an orbit is a mathematical construct, right? So it's the path that is fitted and produces the mathematical description that gives you the eccentricity. But from a physical point of view, you can think of the eccentricity as the velocity or excess velocity coming into the solar system, right? So this very high excess velocity of 60 kilometers per second meant that the eccentricity went not just from 1 to like 1.3 or 1.2, I'm sorry, or to 2. The eccentricity for this object was 6, right? So it's like off the chart kind of thing. But it's because it's coming in so fast. So to answer your question, I think, is speed, incoming speed, past the escape velocity is what determines the eccentricity. Yep.
I think you said something very quickly in passing about comets being created or discovered every 100,000 years or something like that.
Oh, so what I was saying was that even long period comets in our solar system eventually come into the sun and heat up and then go back out. They might be out there for 100,000 years and come back, right? So even that is a short time scale compared to how long 3I has been cruising through the galaxy completely cold. And so those are rapid, 100,000 years is a rapid time scale for a comet compared to 3I, right? That thing has been cold for so long that we don't know how it's going to react. It could be, a spectacular possibility is that there's all of this stuff, hidden, waiting underneath for the thing to get to the right temperature, and it could just like all go nuts. And if, we don't know if it's going to heat up enough to do that. We don't know internally how it's made, but there's a possibility that we're hoping for that it could release a ton of stuff and be a spectacular comet. It's within the realm of possibility. Jeff.
Yeah, you mentioned it's hard to detect near objects on the day side because there's a bright star in the sky. What if you had a total solar eclipse? Could you put telescopes along the path of totality to detect them? So
could you put a telescope on the path of totality to find objects during the daytime? The answer is yes. And so at each location, you've got 2 to 3 minutes to do your observations. And so an issue is how much motion can you detect in 2 to 3 minutes? And so this relates to the question over here of how much information do you need to determine the orbit? And over 2 to 3 minutes, you're not going to get much information. So you need to be lucky in that the object would be visible along that line. But
one follow-up then, could you build a telescope with a coronagraph? Use that.
The follow-on question is, could you build a telescope with a coronagraph and observe that way? I think so, but I'm not sure it would be the most effective way. So the closest thing to that is there is an effort to build a spacecraft to search for asteroids where we cannot see them from the Earth, and that's the NEO Surveyor mission that's scheduled to launch in 2027. And that's going to be inside the Earth's orbit, pointed kind of at right angles to where we can see at nighttime. And so it still can't look toward the sun, but it can see places that we cannot see from the Earth and cover a lot more sky than you can see from the Earth. And basically will solve the problem of not being able to see asteroids during the day. Over here.
Okay, so now we've got the Denneau solar telescope. Is something like that be usable, or would there just be too much light and it would just kind of blow everything out?
So Jeff and I just before this, had a great conversation about whether the Daniel K. Inouye Solar Telescope could be used to detect asteroids either during the daytime, and we didn't talk about nighttime. We would love to use it at night. I mean, it's a 4-meter telescope, right? But I don't think that's ever going to happen. But we did consider, could you see an asteroid and under what circumstances with that telescope during the daytime? I mean, in order to see an asteroid with that telescope, it's got to be going through the field of view, which is always pointed at the sun. And so what you see of the sun is a very, very tiny piece of sky, right? And so it's not really a strategy you would use to search for asteroids. You'd have to be really lucky for one to go through that field of view. And another question is, and we were doing some back of the envelope calculations on this, was how big an asteroid would it have to be for you to even notice it in going across the detector on the DKIST? And we think the answer is that it has to be too big, so that any NEO, any near-Earth asteroid you would care about, it would not be big enough to be able to see with the telescope. Now, that might not be totally true. Someone's got to do like the rigorous homework on that, but we think the odds of finding something with DKIST are probably pretty small. Yep.
You said something about during a solar eclipse to try and view objects coming from the direction of the sun. How about a space-based telescope where you could put like the moon in between the sun and the telescope and keep it there, or the Earth itself? Could you view it for a longer period of time?
Yeah, so the question is other spacecraft possibilities that would have the right geometry to give you more favorable observing conditions, right? So you can see things that you might not be able to see from the Earth because of daytime or whatever. And so one thing about putting something on the moon is the Earth is pretty dang bright. And
not on the moon, but like
behind the moon. Well, so that's kind of where, where JWST is way out there. But it still can't point close to the sun, right? But it can see a lot of stuff. So we think the NEO Surveyor mission is probably the most reasonable effort along those lines, which is you put it inside the Earth's orbit, and it looks kind of away from the sun, but out to the sides of the Earth, and can capture has a nice complement to what you can see from the Earth, and then stuff that from the Earth would be during the daytime. Not like stuff you would be able to see at noon during the day, but at least well into twilight on either side, hours into twilight. So covers, instead of like at nighttime you can see like maybe 60% of the sky. These would get you like 80% of the sky or 90%, all combined with Earth ground-based observations. Any more questions? Yeah.
Kind of a yes/no question. This particular object is off-gassing its coma as a result of the solar wind, correct? And then if it's way away from the sun, it won't off-gas a coma. Is that correct?
So the question is whether 3I is outgassing from the solar wind, and if it gets far enough from the sun, will it stop? Did I phrase that right?
Yeah.
So I think the first half of that question is still an open question. There is a small coma that is due to the solar wind, but it's very small. And the majority of the coma that we see is this thing that's toward the direction of the sun. And what we think that is being caused by is that's the hot side of this thing, right? Or it's the warmer side after millions of years of staying cold. And as so it's rotating, the nucleus, but as it rotates and faces the sun, it's warming up enough that it's releasing some stuff. And so we're always seeing stuff kind of in the direction of the sun. That may change. We think the reason why there's not much of a tail is that the stuff is still kind of, on the non-sun side that's cooler, is still kind of locked down in a way that we don't quite have an explanation for yet. But there's a very, very tiny, tail of stuff outgassing, but it's
But it's the heat of the sun that's causing that.
Yeah, the sun will heat it up, yep, and cause all of this stuff to start outgassing. Yep, that's the way the comets work. Yep.
What do you think causes an object to go so fast as this thing? And what's the kind of, what created in the first place, zooming that fast?
I think the only mechanism, so the question is what causes an object to go this fast, right? And so there's, first of all, there's all of the stars in the galaxy have motions relative to each other, right? So if something were just sitting still, like on its star, as two stars pass each other, they're moving quite fast with respect to each other. So on top of that, now you add things orbiting those stars as they pass each other and possibly being ejected by their giant planets in their solar systems. All of those effects can compound. Once something is ejected from a solar system, it's got to be going pretty fast, right? And so that's the initial kick that gives it that velocity. And then once it leaves that solar system, the odds of it coming close to another star again to be captured are really small, and it just goes forever, basically. And that's what 3I is doing, we think. Yeah.
So, Earth defense.
Pardon me?
What if one of these things comes and is going to hit the planet? Is there any thoughts realistically of what can be done to destroy it? Or
Yeah, absolutely. So the question is, and I didn't talk about it this talk, I usually save it for another talk, is what do you do if an object is predicted to hit the Earth? So I did save some slides, and I'll find those. So let's see here. So a few years ago, you might remember, okay, so here's some concepts for what you could do for a modestly sized asteroid. So let's say one of these 100-meter sized, which is going to be the most likely size that we'll encounter that will be dangerous, okay? So you could try to explode a nuke at the asteroid. It's possible. It's politically, it's difficult. Technologically, it's difficult. It's hard to test, right? You have to worry about you have to worry about a problem. Like you don't want your nuke that you're going to send up to the asteroid to explode on the pad. That would be bad, right? Stuff like that. There's a concept called the gravity tractor, which back when I made this slide years ago was more in vogue, but less in vogue now. The idea there is you park a spacecraft next to an asteroid, and you just actively keep it right like in front of the asteroid, kind of on the side, and that the slow gravitational attraction over years drags that asteroid off of its orbit just by enough. You don't want to move it out of the solar system. You just want to change what happens when it goes by the Earth, right? That's all you want to do. And the final one is this kinetic impactor. And so a few years ago, there was this experiment run by NASA called the DART experiment. And so that was this asteroid called Didymos, which was found about 20 years ago. And the thing about Didymos is this is an asteroid that has a moon called Dimorphos. And Dimorphos is in that 150, 140 meter kind of size regime where we might be able to do something with a kinetic impactor. So the experiment was, Andy Cheng at Johns Hopkins had this great idea where a problem with a experiment to blast something into an asteroid is you have to send a spacecraft there to hit the asteroid, and then you have to send a second spacecraft there to see what happened. And, right, I mean, because you're going to destroy the first one. And so that's expensive from a NASA proposition. And so his idea was, we have this binary asteroid, we can send the impactor into the moonlet, and then observe what happens from the ground and assess the effect that this impact had on the moonlet from the ground. And so that's what they did. So that was the DART experiment. So here is, let's see, is this gonna work? That's my extra slide. Okay, so here's the schematic of it. So here's the DART spacecraft. Imagine a Coke machine going about 5 kilometers a second. Okay, that's the spacecraft. And it's hitting this moonlet, and it's hitting it on directly straight in from its orbit. So it's coming around this way, and the spacecraft is going straight into that. And so what they could measure from the ground is how much did the orbit of the moonlet around Didymos change, right? So they expect that when this thing hits, they know the energy that it's going to impart, and they know before the impact how long it takes the moon to go around Didymos, and they can measure after the impact how long is it going to take. And so what they did was, the orbit of the moonlet was, I think, about 12 hours around Dimorphos before the impact, and the impact reduced it to like 11 and a half hours, which was a much larger effect than they expected. So this kind of demonstrated the feasibility of changing the path of an asteroid of about that size. So it was considered a pretty successful experiment. And one bonus was, so we knew down to the second when this was going to happen. And our ATLAS telescope in Sutherland, South Africa, we stared at this event while it happened, and we made this video. This was all over the internet. So that's the proof of the thing hitting. You can't see the moonlet, right? So this thing's too far away for us to see both objects. But we can see the big dust plume that comes off of the moonlet after we hit it. So it's all dust that's being released. And this whole sequence is like 2 hours long. And the size of the dust plume over here is, so this object's like, it's only a few hundred meters in diameter, but that dust plume is the size of the Earth by the end of that video. That's how fast the dust evacuated. Another question over there.
I've read and watched some shows about using solar sails or like high-powered lasers to try and change trajectory. Is that a thing?
So the question is whether a solar sail or laser.
You have to get it there in its altitude.
Yeah, and a problem with asteroids is that they're rotating. So imagine if you shot it with a laser, that you're kind of hitting a different part of the surface all the time. I mean, it is a slow, very slow momentum you're giving it to it, but if you're shooting it with a laser, it's heating up, and that heat is re-radiating and doing strange things to the orbit as the thing is rotating. So it's a hard thing to model. I haven't seen I'm not familiar with it to know what kinds of conditions you need for that, what's like size of asteroid, what kind of rotation rate might work, and so on.
Basically, those three things are the three best shots, something like that.
Those are the ones that have been explored the most. Yeah, I mean, there's been a lot of ideas out there. There are some folks who think you shouldn't do anything and just wait for it to come in and have an array of things sitting in the atmosphere ready to blow them up into tiny pieces. That's one thought. Yeah.
I thought
Yeah.
NASA was hiring Bruce Willis.
I used to show a slide with Bruce on the red phone, that you just send them up as soon as this happens. But it's yeah. So in terms of movies that are like realistic about the whole thing, Armageddon, not really. Deep Impact, Closer. Frankly, for me, Don't Look Up is sadly the most likely scenario, which is we're not going to do anything at all, and pretend it's not even happening. But the DART experiment, fortunately, was an actual attempt to try to do something and see whether it could work, and was spectacularly successful for an object of this size with enough warning, right? So if you had to do this, if you had a few months to do this, it might be a different story. It might be much harder, right? They had 5 years to plan and prepare and execute this mission, and it worked out. So if you have that kind of time scale and favorable, if it's going to hit, it's going to come close to us. So you don't have to go that far, but you want to do it in a way that gives enough time for the deflection to miss the Earth, right? Question over here.
First of all, I just want to thank you for your ability to explain so much so clearly to those of us who
Oh, thank you.
lay people. Appreciate it. This is not in my area of expertise, but it's been very clear. I was curious about 3I and wondering, is this coming up fairly soon? Is this anything that's going to be visible to regular people with a telescope in the backyard?
So it should be visible to like a reasonable amateur telescope. I think after perihelion, after it goes past Mars and comes around, like in November, we'll be able to see it for a little while. It's not going to be, if it had this tremendous outgassing event, it's possible it could be naked eye visible, but we don't, that's an unlikely thing. But in the realm of possibility, but most likely, small amateur telescope should be able to see it. So you see a little fuzzball on your telescope. Any more questions? One more, yeah.
Completely random, completely.
Random's okay.
When the astronomers are sitting around, does anybody go, I saw the Tesla Roadster?
So,
You want to see pictures? I got
Yeah.
so so in 2016, right after the Roadster was launched, we found a near-Earth object, and it went to the Minor Planet Center's near-Earth object confirmation page, which is where all of the follow-up telescopes go to find out what objects to follow up. And a very weird object showed up from our project, from ATLAS, on the confirmation page. And the gang at JPL, who does the very detailed trajectory analysis, said, there's something weird with your observations. And this object, it looks like a reverse impact, which means that it had a path that looked like it hit the Earth in the past and is still going. And it wasn't until hours later that they realized it was the Tesla Roadster that had been launched from the Earth and was, in fact, something like a reverse impact, right? So it was on this ballistic, right, non-accelerated trajectory off of the Earth out toward Mars, and in fact looked like an impact being played backwards. It's exactly right. So, and we did see it. So when we did that, it was fun to show at the IFA all hands meeting that we saw the Tesla Roadster. It wasn't red, unfortunately, it just was a white dot in our data, but yeah. But thanks, yeah, that's a good question.
One more question.
Okay, well there's two. We'll do two more questions, okay, in front.
I guess for everybody to know, like when you say near Earth objects, is one astronomical unit or more than one astronomical?
So the question is, what does near-Earth object mean in terms of astronomical units from the sun or the Earth? And there's a precise definition, which means that to be a near-Earth object, has to have an orbit whose closest approach to the sun is within 1.3 AU. So that's not quite to Earth's orbit, right? It's 0.3 AU away. It's inside Mars's orbit, but the reason why that number was selected is that it's close enough that its orbit can be perturbed by other planets as it comes into the inner solar system. So even though it might not come close to the Earth on a typical orbit, in the future, the orbit could change enough that it could be a problem in the future. So that's kind of the cutoff that we use that says that this object is worth putting in the catalog, keeping an eye on, because down the road, 50, 100 years from now, its orbit may change from an encounter with another planet in a way that brings it closer to the Earth. A good question, yeah. Because you might think, how near is near, right? How do you decide where to draw the line? That's where the line is drawn. And one more in the back.
Mine wasn't so much a question, it's just a statement. I think that Tesla Roadster thing is just an eccentric bit of grandstanding. As if there wasn't enough junk already in our planet's orbit.
Yeah, I don't know if it's actually, I don't know what the likelihood is of the Roadster hitting Mars. I think it's not likely, or coming back and hitting Earth. Also, I'm not sure, but yeah, it's junk that's out there. But the Roadster in terms of space junk is not the biggest problem. There's One thing about ATLAS is we look at the whole sky all the time, every night. We see all kinds of stuff that's out there. So there's things in like really low Earth orbit, right? Like the SpaceX satellites, your things that you can see with the naked eye. Those are too bright and too fast moving for us. But things out past the geo belt, between the Earth and the Moon, we see a lot of stuff out there. We find old rocket bodies that hadn't been seen, in decades. Other pieces of rockets and satellites floating around out there. There's a problem that is common for projects like ours in space junk is that there's a particular kind of space junk. So you can imagine, so these spacecraft are all covered with these like really reflective, thin, like gold or mylar sheets, right, that reflect the sun off so that they don't heat up. Well, if the spacecraft is destroyed or something bad happens to it, these mylar sheets can be ejected from the spacecraft and they're just floating around out there. And they're so light, but have so much surface area that the solar radiation can push them around. And so their orbits are really unpredictable. And so ATLAS might see one, and we'll be able to get an orbit for it and say, oh yeah, this is probably that piece of space junk we saw last month. But the orbit could change so that the next month we don't know that we're seeing it again. And so it's a problem because when we see these, we don't know what they are, right when we see them. And so other telescopes will go chasing these things, thinking they're a rock, when they're just a piece of space junk. And so keeping track of these things is really hard. And it's a problem in the space junk world. And so, yeah, it's a real nuisance.
Anyone will ever collect all of this junk and recycle it?
I would love, the question is, will we ever clean it all up, right? I don't know. Right now we're making it a lot faster than we are cleaning it up. So that's sad. And there's probably some people here are familiar with something called the Kessler syndrome, which is so imagine you have a bunch of things orbiting the Earth and you smash something into a satellite and now it blows up into a billion pieces, right? So all of those pieces are still in orbit around the Earth, and there's this cloud of debris that's expanding as all of these things evacuate that area. But these little bolts, nuts and bolts and whatever you have are still moving at, kilometers per second. And if they hit another satellite, they're going to blow it to smithereens, right? And so you start this cascade, this runaway effect of one satellite explosion causing many more. And at some point, it's a runaway process that you can't control, right? And so there's debates over whether where we are on that. Because if you don't do anything about it, eventually something like that can happen, right? If you're not careful about managing the debris that's up there, having procedures for how you deorbit satellites, right? So it's a big thing now that when you want to decommission your satellite, you have to get it down in the atmosphere so it burns up and it's not a hazard up there. So the question is where are we at a dangerous point in that cascade, that runaway effect of space trash? And I think it's still a little bit of an open question. Okay, well, again, thank you, everybody. Thanks for all of the questions. I really appreciate it. Thank you, JD.